Today we got more theorems about zeros of polynomial functions. Yesterday we had a couple. Today we got a couple more. Here we go. The first one is called the rational zeros theorem. It says let p of x be this big polynomial right here, right there, where all the coefficients are integers. Consider a rational number denoted by p over q, where p and q are relatively prime. If p over q is a zero of p of x, then p is a factor of zero and q is a factor of the first term. That is very complicated way to say what we're really doing here. Basically what it's saying is all the rational zeros, all the possible rational zeros are found by putting the factors of the constant term over the factors of your leading coefficient. Again, all the rational zeros, possible rational zeros, are found by taking the factors of the last or the constant term over the factors of the first or the leading coefficient term. Better to show you this by example. Look at the next slide. Okay, hopefully this will help. What I'm going to do first, part A says, they give you this big function, and part A says find the rational zeros, then the other zeros, and part B says factor into linear factors. Part B will be no problem once we get part A. Part A is the problem. So this is what the last slide was trying to say. If I'm going to find the possible rational zeros for this one, you take the factors of the last number of the constant term, which are 1, 2, and 4, and you put them over the factors of the first term or the leading coefficient, 1 and 3. So I'm going to take all these factors, 1, 2, and 4, and put them over 1 and 3 to make my list of possible rational zeros. All right, so I'm putting the 1, 2, and 4, and also make sure they're plus or minus because they can be positive or negative factors, and that's fine. So factors of 1, 2, and 4 over 1. So it'd be 1 over 1, 2 over 1, 4 over 1. Now I'm going to put them all over 3. 1 over 3, 2 over 3, and 4 over 3. All right, just like that. Now those are where my possibilities are coming from. And after we make that list of possible factors, I'm going to punch it in my calculator, that function, and look for the zeros, which are really just x-intercepts. So I'm doing that right now, and I punched it in, and I found out that -1 looks like it's a 0. So I'm going to put -1 in my box. 3, -11, 0 because there's no x squared term, 10, and -4. And I'm going to, if it's truly a 0, then I will get a 0 for my remainder. So bring the 3 down, that's -3. Add, multiply, add, multiply, add, multiply, and sure enough, I got a 0. Now, I also saw it looked like it crossed the x-axis between 0 and 1, so I'm going to try 1/3. It kind of looks like the 1/3, and I'm going to try it to see, but this time when I try it, I'm going to use these numbers. I'm trying to break the function down smaller, so instead of using my original function, I'm going to put the 3, the -14, the 14, and the -4, and see what happens with the 1/3. If we're breaking down to 3, 1/3 of 3 is 1. I'm already in trouble a little bit because if I add those, I get that and -13 thirds. What I'm seeing here, there's no way I'm going to get a 0 right there with that fraction. So maybe instead of 1/3, maybe it was 2/3. Maybe I misread my calculator. So I'm going to try that again, except try 2/3 and see what happens here. Hopefully it works better. So I'm going to bring it down to 3. 2/3 times 3 is 2. It'd be -12. 2/3 of -12 is -8. It's looking good. 6. 2/3 of 6 is perfect. All right, so what that does, that leaves me these 3 numbers now. Here's what I know. I know that's a 0. I know that's a 0. What that leaves me with is a 3x squared minus 12x plus 6. Because as I divided, the first time it took it down to an x cubed, the second time it took it down to x squared. So I need to solve that. First thing I'm going to do is I'm going to take out the 3, make it x squared minus 4x plus 2. That will not factor. So you have 2 options here. You can either complete the square or do quadratic formula. I'm going to go ahead and do quadratic. So I'm going to say x equals -b, which is 4, plus or minus the square root of b squared minus 4ac all over 2a, which is 2 times 1, which is 2. I need to make myself some more room here. And so I get this. I get x equals 4 plus or minus square root of 8 over 2. 8 you can break down like this. 8 is really 2, 1, 2. And then I can take 2's out everywhere. My goodness. So that gives me this. 2 plus or minus square root of 2 when you simplify that. And don't forget these 2 answers. My other zeros were -1 and also 2/3. So those are my zeros. That's part A. And you're like, that's part A? That's part A. Okay, then part B says factor into linear factors, which means write them all as factors. So I'm just going to put part B. My factors are, the first 0 was -1, which means I can write that x plus 1. My other one was 2/3. I can write that 3x minus 2. That's slide by slide. I can go x minus 2 plus the square root of 2. and then x minus 2 minus square root of 2. And that's all you got to do on that one. All right, lovely. Let's try, see what we got next. All right, got one more of the same type. I want to make sure I showed you enough of these. This video may be long. It's not many slides, but it's going to take a while. So here we go, part A. Wow, part A. Let's do the factors first. I'm putting the factors of 15, which are 1, 3, 5, and 15, over the factors of 2, which are 1 and 2. So 1 over 1, 3 over 1, 5 over 1, 15 over 1, 1 over 2, 3 over 2, 5 over 2, 15 over 2. Next step, I'm punching this in my calculator, trying to see one that works here, and something works between 0 and 1. So I'm going to try that. It looks like it's 1/2. So I'm going to try 1/2 here. So I'm going to put 1/2 in my box. 2, -1, -4, 2, -30, and 15. It's a bunch of stuff. So bring down the 2. Half of 2 is 1. 0, I like 0. Add, multiply. 0 again. I'm liking this. And half of -30 is -15. So it does, 1/2 is definitely a solution. That's the only thing I could see on my calculator. So what I'm going to do is, that means the other ones must be imaginary. So I'm going to take what I have down here and write it like I have 2x to the 4th now, 4x squared. I skipped the x cubed because of the 0, and a minus 30. I skipped the x1 because of the 0. I'm going to go ahead and take out the 2, which gives me 1x to the 4th, 2x squared, and 15. So what I see something neat already. I know two factors of 15 that would give me -2. I can write this like x squared minus 5 and x squared plus 3. All right, so I'm going to pull these factors over to the side. For example, x squared minus 5 equals 0. If I take the 5 over there, I get x squared equals 5. Take the square root, I get this. X is plus or minus the square root of 5. So here's what I have. Plus or minus square root of 5. Don't forget the 1/2. I'm going to do the same thing with the x squared plus 3 equals 0. Move the 3 over. You get -3. Take the square root. Plus or minus I on 3. Again. Plus or minus I on 3. So there's all my zeros. That's part A. That was actually better than last time. Part B. Let's go part B right here. Right is linear factors, so I'm going to put x plus square root of 5, x minus square root of 5, x plus I on 3, x minus I on 3. And don't forget the 1/2. 1/2 is 2x minus 1. All right, so there you go. There you have it. Wow. Quite a bit of stuff there. Descartes' rule of sign, we're going to end hopefully on an easy note. What Descartes' rule of sign says is that you can figure out how many positive answers and negative answers you should have just by counting sign changes. Like this says, if you have a polynomial written descending order, the number of positive real zeros is either the number of sign changes or variation of signs, or less than that by an even integer. The number of negatives is, you do the same thing, but you plug in negative x, which means you change the signs of your odd exponents, or is less than this by an even number. A zero multiplicity must be counted m times, so if it's multiplicity 2, you have to count it twice. That sounds so difficult, and it's really so easy. Let me show you an example, and then we're done. All right, find the number of positive, negative, imaginary zeros for each. So I'm going to take the first one, part A right here, and all you do for the, I got to find out how many positive it has, how many negative it has, and how many imaginary it has. All right, so all you do to get how many positive zeros it might have is you count how many times the sign changes. It starts positive, that doesn't count as a sign change. It changes to negative, changes back to positive. So there are 2 sign changes. Now the rule said you count sign changes or less than that by an even number. So I'm going to say, okay, that means there's 2 or 0 positive. Now, when you do negative, what you do for negative is you change the signs of the odd exponents in the problem. So it becomes negative 2x to the 5th. That's still negative because it's an even exponent. The x becomes negative, and you never change the constant term. That's why it's called constant. And then you count sign changes again, which means now there's only 1 sign change in the whole problem. So there's only 1 negative. Now to get imaginary, what you do is you figure out what's left. All right, I have degree 5 here, which means I have to have 5 zeros. So if I have 2 positive and 1 negative zero, that means I got to have 2 imaginary because I got to have 5 altogether. Now, if you have, or you could have this, you could have 0 positive and 1 negative. If you have 0 and 1, that's just 1 0, and you got to have 5, which means you'd have to have 4 imaginary. Now, this little imaginary line's got to be even, because remember, they always come in conjugates. They always come in conjugate pairs. Let's try one more. That's really all there is to it. Not really solving them. We're just trying to find out how many positive and negative and imaginary. So part B, last one today. Hang in there. Positive, negative, imaginary. Okay. Positive is how many sign changes. It changes there and then changes back to positive there. So it's 2 again. So I'm going to put 2 or 0. Now, to find negative, I'm going to change the signs of the odd exponents. So that means I'm changing the first term, I'm changing to 3x, and that's all. When I do that, I still just count 1 sign change there. So that means there's only 1 negative. And again, to find imaginary is whatever's left. I got to have 5 again. So if I have 2 and 1, that's 3, which means I have to have 2 imaginary because I got to get 5 altogether. If I have 0 positive and 1 negative, that's only 1. I would need 4 more, so I'd have to have 4 imaginary. And again, imaginary is always even. And that's it. And we'll work on these tomorrow like we always do. Hope it wasn't too overwhelming for you. We'll make it work. See you tomorrow.